Alright, hell yeah. So we're going to do this problem kind of from a guess and check method. I don't even know actually what the equation is to get the answer, because you can do this problem in a couple different ways. There's a range of locations that you can put these books to optimize. But the optimal distance, what we're trying to do is get this top book as far this way as possible. So it doesn't give you any information that these two distances have to be the same, so we're going to analyze that. So this problem, fits my wheelhouse because I'm pretty good at just, hey, let's take a concept that we know and then apply it in the simplest way, get an answer that we think should be good, and then tweak it just a little bit. You know what I mean? And if we tweak it one way and we can actually get this book to hang out more, you know what I mean, without it toppling over, we're good to go. And so, hell yeah. And I even have 3 cassette tapes that we can kind of play around with. Now, if you've ever taken 2 books, this is probably the most important concept, and one of the only ones that we'll be using in today's video. Even if you don't know anything about moments or forces and directions, I'm just gonna say that, hey, look at this. When it's at half the distance, it wants to tip over. You can't push it more. One book, you can't push it more than halfway. What's going on there is that at that point, like, hey, this part of the book has weight, this part of the book has weight, and it's kind of like on a teeter-totter. And so right at that halfway point, it is balanced. But what happens is there is no downward force over here, and there's nothing. There's just air under here. So we just have kind of this perfect balance point where, hey, let's say this book weighs has a weight to it, then my finger has to hold that entire weight. And so that's kind of what's going on in our problem. If we bring this book all the way to the edge, all the weight of this book, so we're going to say each book, we're just going to say has a weight P. And if we bring this top one halfway, then this point is going to feel that load of P at that point. So that's going to be the point that it tips over. For this problem, you know what I mean, I was like, I really didn't know how to solve it. It seems like it's an optimization problem. Maybe find an equation, take a derivative. I didn't want to do that. I just wanted to, so we're going to do the simplest thing. Hey, we're just going to say the 2 bottom books are just stacked neatly together. How far can we get the top book? Okay, we can get the top book halfway. We kind of know that. All right, next scenario. Let's take the top 2 books, stack them nice and neat, and then place them on the bottom book. See how far we can get these. Same thing. We can get halfway, but just a little bit more, and this thing tips over. Cool. So at least D has to be halfway. They say these books are A. I'm just going to say A is 1, just so we can say, hey, this is a length, the whole book's a length of 1. D, in that case, is going to be a length of 0.5. Meaning we can get half the book hanging off the edge. Alright, so I think this is the true magic, is like, what do we do? Like, one thing that I noticed was if I get both of these books together up here, what can I do? Can I move this one farther out? No, I definitely can't. I can move this top book in, but that doesn't help me get the top book farther over the edge. So the only real thing that I can do is actually move this bottom book in. And if that's the case, this is where the optimization happens. It says, hey, if I move this bottom book in just a little bit, like, that means that somehow I can move this top book out. It just has to be. If it doesn't, if that's not the case, then we have found our optimized. Now, not quite. I mean, there could be scenarios like where you make a system that, hey, this is as far as you can get it, but then if I move this book, the middle book in, like, hey, maybe I can't. I can only move this book out equal amounts until something else happens, and then I can get it farther out. But still, I think you kind of get the idea, and we can use kind of the equations. All right, let's get to it. So I'm going to put the lower book right here, and then I'm just going to dot in if they were kind of at this halfway point. So this is this is what we could do. So we're going to say we're going to move this book in, and this is where the first method that I use, I just said, hey, let's just make this a real small distance. I'm just going to say 0.05. But that can get confusing because it's like, well, I don't know where that distance is now. But hell yeah, so now this is the new location of this middle book. And let's put the load on it. So I'm going to put that load. The middle of the book used to be there, but now the middle of the book is right there. So this distance right there is 0.05. Cool. And that's a load P. And so what we know is that this point, when it does tip, is going to have to carry the entire load. This top book does weigh P as well. So this has to carry the load of 2P. And right at its tipping point, it has to act right there. Now, I guess we do need to know kind of what's going on with the sum of the moments. When we get this book to the halfway point, like, hey, we just classically say that the weight of the entire book can be placed right in the center of mass. But that's not what's happening. We have an earth underneath us, and all of this book has bits of mass all over. And so, a couple ways to look at this, probably without getting too technical, you can say like, well, there's half of the weight of the book is over here and half of the weight of the book is over there, and let's say they're probably, and if we split this right in two, they're going to be acting right there. So we could also say that. And those distances are balanced, just like you would have a teeter-totter. Now we have even like the same weight on both sides, and so that's what's keeping this thing from tipping, and it's keeping this balance point right there. So if I had more weight over here, if I put anything over there, I don't have anything that's not too heavy, but hell yeah, it just tips over. And so the only way to actually put weight over there is to move this position. So now I have the same amount. Well, that's not true. I don't have the same. What do I have that's the same? I don't have the same number of molecules over here that I do over here. Yeah. So I guess you do have to kind of talk about leverage. But for our books are like each book weighs the same from the middle of it. Each book weighs the same on both sides. All right, and if we go back to this drawing, like, hey, this top book still weighs a load P, and so if this is kind of like the middle of my teeter-totter, and I have this book a distance of 0.05, and it weighs P, then I could put this top book a distance from this point, 0.05. So that's where I can put this P. And now, you know what I mean? So that's kind of the gist of it, is that both of these loads are even distance from this tipping point. And so this is the farthest. I can't move this load any farther that way. If I could, then I could increase that distance, and we would. But I'm just saying that if I have this lower block 0.05 that way, hey, I get to put this top block 0.05 from this hinge. You know what I mean? Which now we need to see what our distances are. So from here, the center of this top block, and then let's draw this in. The center of this top block is 0.05 from here. And then from the center of the top block to the outer edge is 0.5. So now this total distance is going to be 0.55, and we have increased. So there you go. So that's why I do problems this way, is because you should be able to. You should be able to run through a simple calculation and not mess it up, but then and keep it heady, or not too heady, and just be able to do it. So that's kind of the take-home point, is like if you get a problem and you can't just guess and come up with a solution and do that about 4 or 5 times, then I think that's a skill that you should work on. Like, I work on that all the time because it's just like, hey, like, sure, there's technical equations and technical ways to do things, but at the end of the day, if I can't just shift something just a little bit, analyze it in a very simple way, if I just don't want to do it that way, then that's kind of just like a real bummer on my part. So that's why I always try to do this as much as possible. Okay, so now we're going to, I guess, maybe what are these two distances? So if we move this one 0.05, this one's going to be 0.45, and what's this distance? Well, this is the center of this block right here. This is the pivot point, which is 0.05. This is the center of that block. So this distance is 0.1, and so then we have 0.1 over here. Okay, hell yeah. So then I think the next thing that I'm going to do is just like, well, you know, what if I just take this bottom block and make it 0.1? And I think I actually did this. It's always good just to do that and then take a look at it. So if I make this 0.1 and this 0.1, how does it compare over here? Well, we said if these two blocks were hanging out 0.45, we could still balance them. And so this is good to go. So if all we did was just move these two blocks so this distance was 0.1 and 0.1, heck yeah, this one would be good to go. Okay, so then I thought, well, let's do the next scenario and just move these blocks to this to 0.2, top, bottom, and top. So I'm going to move this block 0.2. So I got a distance of 0.2. This block's going to be 0.2. And this is just kind of a good method to see. And like right now, like, hey, I might not be maxed out, or this thing might tip over. Don't know. You know what I mean? So the weight of this is going to act in the middle. And then the weight of this one is going to act in the middle. So even just right there, just visually, maybe I see that, whoa, both these loads are on this side of this pivot. I know when this thing's ready to tip, I'm going to have an equal load over here as I will over here. And not necessarily equal load, but equal distance. So, and in this case, since the books weigh the same, if this book is over here, then I have to have an equal load on this side due to this lower book. Alright, but I thought this problem was good to actually like be able to find these distances. So I'm going to say like this is kind of my origin, and in all these problems we kind of want to know what this distance d is. And I'm going to say all these books have a length of 1. The center of mass where these loads are applied is a distance 0.5. So what I want to know is, hey, what's just this distance from there to there? You can call it x. Sometimes I just like to do a box. And then, so from this problem, I gain this insight. If I start here and I go this direction, I'm just going to call this the positive direction, because when I get to here, I'm going to get a positive number. You know, if I said this was the negative direction, you know, this is kind of an axis. If this is my x-axis, and I call this negative and this positive, then hey, this is on the negative side of this axis. So I'm for sure going to call this positive and this negative. So I'm going to go positive 1, negative 0.2. So positive 1 minus 0.2, and I'm to this point. You know what I mean? And where are we trying to get? Well, we're trying to get to this point. Okay, well that's just half this distance of the block, so I got to go negative 0.5. Now, I spend a lot of time on this, and this is the one technique that I see that happens a lot in trigonometry. Where it occurs in trigonometry is, hey, let's say I have this triangle, and it's like two right triangles. I know this is 10, and this is 2 over here. What's this distance? Well, you know what I mean? Like, who knows? But I can say I'm going to start here, and I'm going to go, and then the same thing. Let's use that same technique. Hey, this is my x-axis. I could call this the positive x, but that would be dumb, because I'm going to go negative 10 and then plus 2, and then I would say I'm already in the negative. So I'm going to call this the positive x direction and then the negative. Now, I'm just repeating what I did here, but this is kind of, this is a better visual to do it. Typically, what I just say is like, what's this distance? Well, it's going to be 10 minus 2. So if I, and that's a little bit harder to see, you know what I mean, where this happens all the time in trigonometry. You know, you have something like this, and you're just on the spot, have to know, like, what that distance is. And, well, that distance is 10 minus 2. And then when you have variables, it's even worse, because you're saying, hey, this is a distance x, I don't know it, but I do know what this distance is, 10. Now, do I know anything about this distance? Well, hell yeah, same thing, 10 minus x. You know what I mean? But that's a little bit trickier. So back to here, we're going to say this is the positive direction. I'm going to go 10 in the positive and then minus 2, and that's going to put me at this distance. So that kind of treats this as a vector, and I think that can be useful. Okay, so what did we find? We went 1 minus 2 minus 0.5. That's going to be 1 minus 0.7. Sorry, and we get positive 0.3. So this distance is 0.3. Now let's find out what this distance is. You know what I mean? So we're going to go 1 in the positive. So let's write our equation. 1 minus 0.2. So we went 1 minus 0.2 minus 0.2. And what are we trying to get to? That point. So minus 0.5. You know what I mean? And again, positive 1 minus 0.2 minus 0.2 minus 0.5. And then good is also good to do it again in a quicker way. What do these add up to? I don't know, 0.9. So I'm going to go 1 minus 0.9. So it's going to be 0.1. So cool. So this distance is going to be 0.1. So now both my forces, this is going to be 0.3. I got a force 0.3 away from my tipping point and a force of 0.1 away from my tipping point. Again, we're good to go. I don't think this puts... Now we want to know what D is, you know what I mean? And we're going to play that same game. So it's just like, well, how do I get out to here? Well, and let's flip our, if we kept with this is the positive direction and this is the negative direction, by the time we played that game and got to here, we're going to get a negative answer. You can do that and just know to switch it, because like obviously this is some sort of distance, and a negative answer doesn't make sense. But let's switch this. So I'm going to say this is the positive direction. Now this is the negative direction. So let's do an equation. I'm going to start here, and I'm going to try to end there. All right, so I'm going to go negative 1. And now I'm going to go in the positive direction. Plus 0.2. Plus 0.2. And now I'm going to go plus 1. Cool. This whole block is 1, or book. So I'm going to go negative 1, plus 0.2, plus 0.2, plus 1. Hey, so negative 1 plus 1, let's kind of cancel. So my distance is 0.4. Cool, so we got 0.4. You know what I mean? It wasn't optimized. That wasn't we were just kind of throwing it out there. You know what I mean? And again, like if you're not able to do a problem like this like 4 or 5 times and just like slowly like try to crawl to the right answer, I don't know. I think having patience to do this, and it really helps your skills of like not making like little tic-tac mistakes. And so we're going to continue on. Let's boost this up. So all right, so we got our lower book, and none of this, we really don't have to draw it to scale. I'll try to draw it to scale fairly, but we're going to do 0.3 here, and then right here we're going to do 0.3. So at the midpoints we have the weight of the books. And I don't even know if I drew it to scale. I don't know where this is. I'm just trying to get it halfway. So what I want to know is that I want to know this distance from this axis, and I want to know that distance. And these are the only 2 loads. The books have the same weight. I mean, if you change the weight of the books, that would change the problem. If this book weighed twice as much, you can't get it as far because it's really wanting to leverage. The whole point of the teeter-totter is if I have even people on both sides that weigh the same, then they can just balance. But if this person is heavier, just with a bigger head, I guess, then if this is twice as heavy, then I gotta move this thing, And this is where you use that sum of the moments. This is why this problem is cool, because you really don't have to know too much about moments. You're just saying, hey, I have these two people or these two books, and when I have them, when it's balanced, like they better be the same distance on either side. If this distance is way far this way, well then I could have just moved the books. So it's like, even if we go back here, you're just like, well, like, yeah, this is cool because there's many ways to do a problem. Because didn't we say, like, hey, we moved this just a little bit? Hey, we got a distance of 0.55, and that was balanced. But then we said, hey, we could just move this way as much as we wanted. And we could do this to our problem. Okay, and so why not do the opposite? Why not take this and then move it out to its optimized position? You know what I mean? And so let's do that right now. So what did we say that this distance was? 0.3. What did we say this distance was? 0.1. So we have a total distance between these 2 points. All right, hell yeah. So the distance between like the weight of these two books is going to be 0.3 plus 0.1. It's going to be 0.4. And we're going to say that, hey, we're going to put the teeter-totter right in the middle of two things that weigh the same. Hell yeah. So we got to put that, we got to put them 0.2 and 0.2. Okay, so sweet. So now we're gonna let's redraw this one just one more time and see where we're at, because we get to play kind of this game to figure out. So right now we know that we can move both books that direction. Just like once we optimized it, we could have just moved both books inward, and then they're going to be hella stable. So we're taking this and we're moving it out. The distance between these don't change, so this top book, let's do that. So this top book always remains 0.2, so we get 0.2 there. But now we're going to take this 0.2. Wait. So we have 0.3 on this side, 0.1 on this side. We want to get 0.2 on this side and 0.2 on this side. So we need to move this one. We need to move this whole system 0.1 that way. So sweet. So we're going to have 0.3 here. And now let's see what this distance is. I think the hardest part of this problem is just like, hey, figuring out, using all these little dimensions, knowing that, hey, maybe your loads are 0.5 away, these distances are 1. But now we can see that, oh, heck yeah, I can start here. I want to end right there. And hopefully that's going to be the positive direction. So I'm going to go -1 plus 0.3 plus 0.2 plus 1. All right, heck yeah. And I'm sure there's easier ways to visualize that, because it's almost like one of those relativity problems. Like this distance 1 gets canceled. So yeah, that's kind of fascinating. That it's literally... but hey, well, what's this distance? Like, honestly, I couldn't tell you, so let's play that game again. If this is the positive direction, I'm going to go -1. So -1 plus 0.3 plus 1. Okay, so now I can just see this is 0.3. I don't know, it's like sometimes when you get into the equations, it's harder to see stuff that's just like, whoa, that is like stupid intuitive. But that's the issue with like statics and math, is just like there's an intuition that, no duh, if I pull this one 0.3, this distance opens up 0.3. But when you use it as an equation, it's just like it might not seem so intuitive. Okay, so let's figure out what this distance was, and it was so we went -1 plus 0.3 plus 0.2 plus 1, and we get 0.5. Okay, so in this scenario, when this is 0.2 and this is 0.3, hey, we have another scenario where we're half the distance. So it's not super optimized, not optimized at all, but it's just fascinating. This scenario where we went a third and then 20% was just as good. Now see how this is halfway? That's fascinating. Let's do this one. Yeah, so whoa. No, this one should be optimized, because if we did that, now let's go see where these loads are from this axis. we should be able to do that. So where is this load? It's going to be, what positive distance is this? So we're going to go positive 1 minus 0.3 minus 0.5. So that distance is going to be 1 minus 0.8. This is going to be 0.2. And that's what we thought. So that load is 0.2. Where's this distance? Where's this load? Well, we're going to go, and we want that to be a positive number. So we're going to go negative 1 plus 0.3, 0.2 plus 0.5. So that distance is, yeah. No, so yeah, we didn't move this enough. Yeah, I don't see how we messed that up. Oh, you know what? I think when we did this, both of these loads were on that side of this axis. Okay, hell yeah. So I'm gonna slow this one down just a little bit. And this is the whole nature of doing these problems. If I can't do it like fast and a bunch of the same problem, then it's kind of like, for me, it's like not worth getting a technical solution. So 0.2, we have a load here and a load here. I want to know, so this is my tipping point. I want to know, are both these on that side? That was kind of the question. I didn't know. So I guess if they are both on the positive side, I'm going to have, so let's do this one. It's going to be 1 minus 0.2 minus 0.2. I'm sorry, slow down. So to get to this point, I'm going to go 1 minus 0.2 minus 0.5 to get the center of that one. So that's going to be 1 minus 0.2 minus 0.5 and 1 minus 0.7. So we're going to get 0.3 right there. Okay, hell yeah. So to get to this one, it's going to be 1 minus 0.2 minus 0.2 minus 0.5. So this is 1 minus 0.9. So this load, I caught my error. This load is still on this side of the teeter-totter. So if here's my teeter-totter, and I have a distance of 0.1, and then 1, 2, 3, and then a distance of 0.3. So here's my loads right here. So this is 0.1 and this is 0.3, and so I can get these loads. So they're yeah, and that does change things, because now the distance between these two is just a distance of 0.2. So then I can get these loads 0.1 on this side and then 0.1 on that side. Alright, hell yeah. And now I can optimize the problem. So I'm going to redraw. And it might not be the most optimal, but like I said, I'm just taking something that works, and then moving it. I'm just kind of playing around with a problem. And it's good to do that using the math and using the equations. It's the same thing as doing this. You know what I mean? 0.2 and 0.2, and then we're just going to shift the whole thing, and you be the judge. Hey, do you think this is 20%? Hard to tell, but I think that's about, like, if this is half, this is a quarter, this is about 20%. And now let's see, and then this is halfway. So let's see if I get it halfway. Okay, it's balanced. Can I get it farther? Well, sure. So it looks like I can get it farther from this. So now let's use the equations. So now what we're interested in is moving this. How far can we move it? It was out here. We're going to take the center and put the center right there. So we can move this 0.2. So I'm going to have 0.4 right here. And I guess this is 0.4, no duh. And then this top one still has to be 0.2. Okay, and now let's figure out where the centers of things are. I'm assuming that this one is on this side and this load is on that side. So we're going to use that same technique to find that distance. This is going to be the positive direction. I'm going to go positive 1 minus 0.4 minus halfway is where this load acts, so minus 0.5. So that's going to be 1 minus 0.9. Heck yeah, this is going to be 0.1. and we're getting numbers that we thought we would get. Now over here, I want to know this distance. So I'm going to say, hey, that's going to be a positive. I'm going to say this is my positive axis. This is my negative. So I'm going to go -1 plus 0.4 to get to here, plus 0.2 to get to there, and then plus 0.5. So I got 0.9, so I got 1.1. So these add up to a positive 1.1. So -1 plus 1.1 is positive 0.1. Sweet, and we get what we would have thought. All right, but now the question is, what's this distance? Now, same game. You know what I mean? We want this to be a positive number. I'm going to start here, and then I'm going to, and you don't, the interesting thing is, like, you don't have to, I'm starting here. I could start, well, I mean, you could start up here. Let's do it both ways. You know, I can't start right here because that's who knows where that point is. But if I'm trying to find this distance, I can start here or I can start there. So it's just kind of fascinating that you can do that. All right, hell yeah. So let's start here. We want a positive number to get to our distance. So I'm going to go -1 plus 0.4 plus 0.2. And then plus 1. Booyah. These cancel, and we get 0.4 plus 0.2. So we get 0.6. And again, we now, this is super cool. This is why I do this stuff, to be like, well, no duh. I don't see it on paper. But yes, if I have this and I move this 0.2, obviously, by the definition of maybe rigid bodies, I have no idea. But yeah, rigid body says if I move this rigid body, if I move this point of the rigid body that way, every point on this rigid body moves because it doesn't squish. You know what I mean? So that's it's always good. No professors, they just say the word rigid body, but I had to look it up, and I'm going to try to use that every time. It's just like the definition of a rigid body is if I take this point on the rigid body and then physically lift it and move it that way, every other point went along with it. You know what I mean? So if I just move this point in this x direction, every point on it moved that. So there you go. That's a proof of, like, if I move this 0.2, booyah, we got 0.2 there. But I can't see that. You know, I can't just look at this drawing and be like, if I know that's 0.4 and 0.2, but now I can, and now in the future, I'll be like, hell yeah, 0.6. But for the life of me this morning, until right now, did I not see that correlation. All right, but hell yeah. So let's say I was saying that we could even start here and end here and figure out our distance. Same thing. I'm going to start here. This is my 0. I'm going to say this is the positive direction. So I'm going to go, and, I mean, if I already knew these, duh, 0.2, 0.4, we got 0.6. But if I didn't know these, you know what I mean? I'm going to go 1 plus 0.2 plus 0.4. I'm to there, -1. -1. Yeah. So this is the positive, the negative axis. And we did it. Ones cancel, and we get 0.6. So hell yeah. So we're doing pretty good so far. So we actually found a scenario where if we do this one, if we put this one, so if this is half, quarter, just a little bit, 20%, let's say, hey, we can move this to 0.4 and rest it right there. And hell yeah. And now, I wish I had another one of these, but you can see the center of this is right there, the center of the cassette, and it sticks out more. This is the pivot point. This is the lower book, and you can see how much is sticking out. So super cool. All right, so now we're going to work on just keep optimizing and kind of keep doing the same problem because it's very useful. All right, hell yeah. So the next one up is 0.3. And so we're going to go through that same process. Could we do it a different way? Could we do it faster? Now that we got some techniques, what's this distance? I don't know. You know what I mean? I'm going to, well, let's start from this point. You know, we want this to be the positive direction. What do I know about this? Well, I know it's 0.3. So I could say, and this is the negative direction. So I'm going to say I'm going to go negative 0.3 this way. And then I know that this load has to happen in the middle. So this is 0.5. So I'm going to go negative 0.3 plus 0.5. always good to do things like once you get the hang of something, see if you can use it in a different way. So yeah, this is going to be a distance of 0.2. Now I for sure just can't see that right away. Like even over here, what's the distance from this one? Don't see it. But let's play that same game. If this is, we're going to start here, and I'm just going to assume it's going to be in this direction. I'm going to call that the positive direction. So we're going to be 0.3, 0.3. So I'm going to go 0.6 this way, and then minus 0.5. Now I can even do that in my head now. So 0.6 minus 0.5, this is going to be a distance of 0.1. Alright, hell yeah. So I know that this distance is going to be 0.1. What did I say this one was going to be? 0.2. And let's do this one more time. I'm going to be minus 0.3 plus 0.5. So yeah, 0.2. Alright, same thing. This load is more on that side. If this was a teeter-totter, we could put it at the 0.15 mark. This says this distance is 0.2, and then the teeter-totter 0.1, and so we have a total distance between these two loads of 0.3. So if we move this, well, and then even right here, like what's this distance? I mean, it should be juicy, and we can see that it's 0.6. You know what I mean? Now that we have that reference point, I can easily see that now. If you wanted to do it the long way, we would say this is the positive direction, minus 1 plus 0.3 plus 0.3 plus 1. So minus 1 plus 1, those cancel, and we just got 0.3 plus 0.3. And this is very good because, especially with dynamics, is you have to do everything with vectors. You know what I mean? You have to start at an origin and then go out to something. And yeah, especially when subtracting vectors, I'm for sure going to make a video on that. That's literally why I'm doing this, to get better at subtracting vectors and better at visually understanding what it means to subtract vectors. Alright, hell yeah. Because subtracting, and just the general, like what am I talking about? Like what's, if this is A and B, what's A minus B? You know what I mean? Like no one knows. But it's the same thing as A plus vector B going in the opposite direction. Well, why don't you say so? Okay, now I know how to add vectors. So if this is negative B, I can add these. Hell yeah, that's just what we work on, is the parallel. You know, I'm going to start here, go there, and then tip to tail it. You know, and then I'm going to end there. Or I can go this way and then tip the tail it that way. So I'm going to, you know, or, you know what I mean? And for sure, this will be my resultant. Like, hell yeah. So I'm going to start here, end there. This is my A plus. This is my A plus negative B. But guess what? That's going to be A minus B, which is, bizarrely, if this is A minus B, I go to B and then work my way back to A. But you know what I mean? When professors just say that's the case and you don't spend a whole year trying to analyze why that's the case, it's just like, it makes no sense. Anyway, moving on. Okay, so we have optimized it, but P is still that way just a little bit. So what can we do? Now visually I can just move this thing. If this is 0.2, this is 0.1, I can get this distance to 0.15. I can move this thing this way, a distance of 0.05. So hell yeah. So I'm not going to do that, but we can just say, hey, D could be 0.65. And now we're getting better and better. Okay, so now we're going to choose one that probably breaks the bank. And this is the whole process that I went over this morning. And you know, I didn't know what was going to be optimized. I could have guessed a little bit, but honestly didn't know. So I threw in 0.4, and usually you get to a place where it's just like, no, that's too much. It's going to tip over. Alright, hell yeah, but now we can really speed through things. I know this is 0.4. I know that the loads happen at the halfway points. What I'm interested in is this being my pivot point, this distance of that load compared to this distance of that load. These loads are the same, and even if I drew this to scale, I can just see, hey, it looks like that one's going to be bigger. Okay, so let's do it, and we're going to say this is the positive direction. I'm going to go 0.4 plus 0.4. Hey, I'm going to go 0.8 minus 0.5. See how this is 0.5? And now I can just do that kind of fast. To slow it down, I'm going to say this is a positive direction. I'm going to go 0.4 plus 0.4 minus 0.5. That's going to be 0.9 minus 0.5, and I'm going to get a distance of 0.4. So this distance is 0.4. And I did it wrong. I don't know why I said 0.4 plus 0.4 was 0.9. That's 0.8 minus 0.5. This is going to be 0.3. Sorry for that error. Okay, what's this distance? It looks small. So we're going to go, hey, 0.4 minus 0.5. See, now we can just do it just much faster. I'm going to say this is the negative direction, negative 0.4 plus 0.5. But even just doing that, it was just like, hey, I could say just 0.4 minus 0.5 is negative 0.1. And I just know that this is a geometrically absolute distance. You know what I mean? So a negative distance doesn't make sense. But hell yes, definitely better to be like, I think this is going to be a positive distance. Let's make this my positive direction. This is the negative direction. I'm going to start here, negative 0.4 plus 0.5. And that's going to be a positive 0.1. Sweet. So I know this is going to be positive 0.1. All right, so this is not optimized, and this will just tip over. You know what I mean? Because the distance between these is 0.4. I would have to move this whole system this way by 0.1. Let's see what the distance would have been. The distance would have been 0.8. But now I can move the whole system that way, and if I do, I would have to move it a distance of 0.1. So I could get 0.7 if I just said that this was 0.3 and this was 0.4, and now so this gives me a distance of 0.7, and that might be the best answer we've had so far. So that's fascinating. Yeah, that's fascinating to me. Alright, hell yeah. So we're going to do this probably a couple more times. But now that we know that 0.3 was undershot and 0.4 was overshot, now we you know, this is a good time to work on your decimal skills. So we know it's somewhere in between. Hey, maybe it's just, you know, a third. Maybe it's 0.333. So what we're going to do is, yeah, just try that out. So I'm going to go a third and then a third. And hell yeah, let's just use all our skills that we've learned so far. We have this load in the middle, this load in the middle. I want to know what this distance is and that distance is. This is going to be a third and a third. This is going to be the positive direction. So let's try this one. I'm going to go yeah, the positive direction. I'm going to go negative 1/3 minus a third and then plus a half. And this is really good skills. You need to get the denominators to be the same. So let's do that. Let's make this denominator 6. We would do that by multiplying top and bottom by 2. You know what I mean? So then we got negative 2/6 minus 2/6. So for the simple ones, yeah. And then what would this be? This would be 3/6. You know what I mean? So you can just kind of intuit that. Or you can be like, well, 2 times 3. And then multiply top and bottom by 3. That's just like multiplying by 1. And so you get 3/6. So now we got, and then anytime you do this could be the square root of 3 down here. It wouldn't really matter. This is where I just call this oranges. You know what I mean? You have something funky going on, but as long as the denominators are the same, you're just ready to rock and roll. You could have square root 7 right here. As long as you had them all, like you're just saying that these are oranges. So I use the orange analogy and be like, hell yeah. So now I just visually can see that I have negative 2 oranges, minus 2 oranges, plus 3 oranges. Looks like I got minus 4 plus 3 oranges. I got minus 1 orange. And back to what it was 2/6 minus 2/6 plus 3/6. So now I can see, hey, I got minus 2 minus 2. So I got minus 4 oranges plus 3. That's going to be negative 1 orange. Don't forget to put what the hell the oranges back are. You know what I mean? If it was this case, it would be negative 1 square root 7, 6 square root 3. But that's a really good way to just to see that. Like you're kind of factoring it out, getting the hell out of there, but just keeping it in and just calling it an orange is my current strategy. I've been digging it. Alright, so this distance, we thought we were going to get a positive. What? Oh, did we mess up? Or maybe I did this problem wrong. So we have 1/3. Oh, yeah. Oh, bummer. All right, nope. I just made a hell of a mistake. What we found was this distance. So it's always when you make a mistake, unless it's just like real dumb, you know what I mean, and most mine are. But it's always interesting to analyze your mistake because sometimes your mistake is something in reality. So it's just that you, like for me, that I just did it. What I did is I started here. I called this the positive direction, and I went negative 1/3, negative 1/3. I didn't realize I was over here, and then I went a positive 1/2. So what I did is I got to this point. And if I called this the positive direction, then this point is in the negative, axis. So I'm saying that this distance right here is at negative 1/6, which means that it's over there. So that's where it is. If I want to know what side of this kind of pivot point I'm at, well, it's going to be over there. So I just know that, and so let's do this one. Well, let's redo the mistake. So we're still going to call this the positive direction. How to get to this point? I'm going to go I'm going to go minus 1/3, and then just plus 1/2 to get to that point. And then so that's going to be this point on this axis. And that point on this axis is a distance away from 0. I don't know. I think that's good. I'm seeing correlations here between vectors. Yeah, it's just fascinating. I just don't have the I like to do it, but I have a hard time explaining the technical details. But I can see what is done from a technical perspective, and I really enjoy just kind of like going through the motions. Really good to get it dialed in. So hell yeah. So negative 1/3 plus 1/2. What's this? This is going to be negative 2/6 plus 3/6. Negative 2 oranges plus 3 orange. I'm going to get 1 orange, 1/6 an orange. So this distance is 1/6. Let's do the positive. So we're going to say this is the positive direction. We want to know if this is our axis at the origin. We want to know how far that is over that way. So I'm going to go positive 1/3 plus 1/3 minus 1/2. And it's probably good to either, if you know you're going to do a problem where everything's going to be a denominator of 6, I can call this distance 6/6. I can call this 2/6, and 2/6, and I can call this distance 3/6. So if you do that, same technique applies. It gets a little bit like, I hate fractions, but still just call, just pretend like they're all oranges. So what you're really seeing here is, and this is the positive direction, what you're really seeing here is 2 plus 2 minus 3. Okay, hell yeah, that's just 4 minus 3, that's 1. 1 what? 1 orange, and then you get there at 1/6. So, and if you went, let's say we went this way. So we're going to say this is the origin, this is still the positive direction. So we're going to go negative 6 oranges. Oh, we got to get all this the same. So this is 2/6, 2/6, and then halfway is 3/6. So I think you see it, but yeah, this distance is 2/6, 2/6, and then we got 3/6. This whole length right here is 6/6, and then you can see that if you just consider these oranges, then hell yeah, this is the negative direction though, and we're trying to get to here. So I'm going to go negative 6 plus 2 plus 2 plus 3. That sounds like negative 6 plus 7. You know what I mean? There's 5, there's 2, there's 7. So negative 6 plus 7, that's going to be positive 1. Positive 1 what? 1 orange, and we got a distance of 1/6. And hell yeah, and we're balanced. We got a distance of 1/6 there, a distance of 1/6 there, and now we're perfectly balanced, and we want to know what this distance is. And the problem isn't over because we do not know if we're maximized. We think we are, but now we have to, then we have to tweak something just a little bit to see if we're maximized. And that's what I did this morning, so that's what I'm going to show you right after we get this distance. So let's do it. Let's figure out what this distance is. Well, it's going to be really easy. 2 oranges plus 2 oranges, that's 4 oranges. What the hell is the orange? It's a sixth. So we got 4/6, and that's our distance. Did we do it right? I feel like that's not what I remember, but yeah. So that's 2/3. Okay, yeah. So we can get it 2/3 over the edge. And let's go back to our pic. Let's say this is a third. I can see that this is a third. Are we hanging on for dear life? Hell yeah, we are. So and do you see a third in all those? I think you do. So that kind of visually proves that booyah, it's a third and a third and a third. And then oh, this is fascinating. I messed up. Somewhere I messed up this morning. Either in my assumption, because I didn't know if this problem had more than one solution. But no, it only has one solution, I think. So I can kind of see that if all these are a third, like I can't move anything. Well, the question is, can I move this way to get this thing more that way? And I don't know. You know what I mean? So that's going to be the next question that we do. If we get everything to be a third, like how I can test for optimization is that, well, what's the only thing that I could do? Like I can't move this way any, so we're going to play that same game. Like, can I move this one just a teeny bit, knowing, and then seeing if I can move this one a teeny bit more? Because that would make this move that way a little bit more. So that's what we're going to analyze next. Alright, hell yeah. So now what we're going to do is that same technique to see if this is the only if this is the best optimization that we can have. 1/3, 1/3, meaning this distance is a third and a third, or 2/3. So how do we do that? Well, we have to see what we can and can't do. What we can't do is just move this one this way, the whole thing will just tip over. So we can't do that. What we're trying to see is if we can move this one this way and then somehow move this whole system out farther. That doesn't seem quite logical, even just intuitive. So the other scenario is like, well, let's move this one back, and if we're able to move this one back a little bit, hey, maybe we can push this one twice as far. Hey, it even seemed like I could do that. You know what I mean? So those are the two. So how do we mathematically model that? So let's get this bottom book. We know this is about a third. I'm not going to write any numbers in, but I'm going to say, hey, what are we going to? So what was the top scenario? I'm going to go. Let's do that one first. It didn't. Which one seemed more logical? So they're both at a third. I'm going to move the top one in and try to move this one out. Okay, or I could move this one out and then the top one in. So I guess it doesn't really matter. So let's just draw both of these scenarios, and then we'll analyze them. So we're going to say this is 1/3 plus. Now I'm just going to use a variable x. I think we can handle it. And then this is going to be 1/3 minus x, and x is just a small amount. And if this is the case, then we're going to see where our points are. And then so over here is going to be 1/3 minus x, and then 1/3 plus x. Now, if we do this, this isn't going to give us like the optimal position, but it's either it's going to give us something that we can then kind of tweak and see if this distance gets bigger. So let's try one. And I think I'm just going to use kind of decimals for this. I know this is a third, so we're going to use our calculator too. And how much should we change this? Like what's a third? It's 0.3, so let's change it 0.01. So just kind of hardly any at all, we're going to change it 0.01. So now we want to know what these locations are, you know, and this is good because now we're just doing it kind of from a analytical, seems kind of mathematical perspective. I mean, these are numbers, a third plus 0.01, and this is going to be 1/3 plus 0.01. So that's kind of what we have going on. So let's, and this is our equilibrium. This is our, you know, this is going to see twice the load. And right at tipping, these two books have to be equal distance. Now they're not going to be, but then we're going to tweak it to make sure they are, and then we're going to check that distance. And if it improves from 2/3, we're going to say, hell yeah, we can optimize it. If it doesn't improve, then we should say, then we should be able to prove that 2/3 is optimized. So this is kind of using the method of like, hey, if you think you have an optimization, well, shifting it just a little bit, changing one thing just a little bit should make everything worse. And changing a direction the other way should also make it worse. So you've kind of hit an optimization point, kind of like a maximum. Hell yeah. All right, so what were we trying for? Kind of this distance. So we're going to call this the positive axis. And I want to get to that point. So I'm going to go plus 0.1. So I'm going to go positive 1 minus a third, and then this is going to be a point, also a 0.01. So we're going to go minus 0.01. Okay, so for this next one, I'm going to go. So I went plus 1 minus this, and then I got to go minus this. So that's going to be minus a third. Now it's going to be minus a third minus 0.01, but that's going to be minus a third plus 0.01. Now, I hate negatives, you know what I mean? But if I have to subtract this, a few ways to do it. So let's look at this. So if I have to subtract this quantity, 1/3 minus 0.01, I could think of it like this. I could think of it as adding parentheses and multiplication of -1. This is the same thing, and this is kind of useful. It's just like, ooh, I like to add things, but I would have to factor through a negative. So this negative can indicate this little system right here. So I'm going to factor this through. I'm going to be a positive -1/3 plus 0.01. That's the same thing. And now if I add this whole thing, it's the same thing as adding a -1/3 plus 0.01. So I think that's an easier way to look at it. I don't know. I mean, I don't know what you do when you get to this, adding a negative. I think that's easier than subtracting a negative. You know, adding a negative, I think I can handle that. But yeah, so do this in all-in-one motion. We're going to be adding 1, subtracting a third, subtracting 0.01. Then we're going to be subtracting a third. So let's just write this. Subtract a third and then add 0.01. Cool, now we're to here. Where are we trying to get to? We're trying to get to, and again, I apologize. We don't even know where we're going. I'm going to start here. I'm going to end right here. So I'm just going to add 1 and then subtract this amount and then subtract 0.5. So there you go. So we're going to add 1. Subtract a third, subtract 0.01, and then add 0.5 plus 0.5. Cool, and we're just going to get a decimal answer for this. But we have 1 minus, 1/3, I'm going to store that as x. So I have 1 minus a third minus 0.01 plus 0.5. Sweet, so we get 1.156. Repeat. Alright, hell yeah. So that's, I think something's wrong here. Yeah, what up? So we had positive 1 minus a third minus 0.01. I'm sorry. This has to be minus 0.5. Yeah, we're going in the positive direction, and then this is in the negative direction, to get there. The answer that we get is this positive number from this axis. Hell yeah. So, one more time. And so we get an answer of 0.156. Repeat. Cool, we're going to do the same thing up here. And, alright, hell yeah, let's do it. So we're going to call this the positive direction. Two ways we could do it. We know that what this distance is, these two distances are the same over there, but let's go this way. We'll go here, 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 and then subtract 0.5. So we're going to go, this is the positive direction, this is negative. We're going to subtract 1, add a third plus 0.01, and then we're going to add a third. Now we got to add a negative, so we're going to subtract 0.01. It's just way easier to visualizing adding a negative for whatever reason. And then we're going to add 0.5. So that should do it. Subtract 1, add all those things, and let's see. Alright, let's just do it in our calculator. So we got negative 1 plus a third plus 0.01 plus a third minus 0.01 plus 0.5. Cool, and we get 0.16. And that's going to be 1/6. Okay, hell yeah. So we'll see if we're, we'll see what's up. So now we have this distance as 0.16, and this distance is 0.156. I'm going to store this distance as B in my calculator, and that distance is A. So this is going to be, 1/6 is going to be B. That other distance, this 0.156, repeat, is going to be distance A. So, hell yeah. The total distance between those, alpha A plus alpha B, is 0.323, and I'm going to store that as alpha C. So the midpoint of like kind of the teeter-totter can be this distance, and so we're going to divide by 2. I'm going to store that as alpha D. So then these two loads, because this one was farther that way. So one thing that happens is that if this book is farther that way than this book, it just don't work out. This thing will tip. I have to actually move this whole system back, you know what I mean, to where it's this equal distance. And so if it's this equal distance divided by 2, in my calculator I have that as 0.1616. This is the distance that, this is as far as this load can be. And in the problem, I have it out here at a 6th, 0.166 repeat. I have to bring it back to here. So this is B, and then this is D. So I'm going to say alpha B minus D. Store that as alpha E. I got to bring that back 0.005. So just to let you know, I got to shift this whole thing this direction 0.005. But maybe, I don't know, maybe we just are still optimized. Who knows? So one way to do it, I mean, I could shift it right now, but let's just figure out what D is in this scenario, and then just know that we have to reduce it by this number. And so, cool. So we're going to start here. To get to D, I'm just going to add this and add this. So I'm going to say D is a third plus 0.01 plus a third minus 0.01. Oh yeah, no duh. And I kind of see that is going to be 2/3, which was our optimized position. But in this position, it's going to topple over. I actually have to reduce this 2/3 minus 0.005. So this scenario, by shifting 1, I don't get any extra juice out of the other. And so, and now I'm actually noticing that because there is no difference in these, in P, in the loads of the book, that shifting one, won't really help anything. And in this scenario, it actually worsens. So this scenario made it worse. So let's try this one and see if we can make it any better. Alright, hell yeah, last round. So we just did this one, and we just flipped the parameters. I can't imagine it'll be any different. But let's do it, just because it's good practice. So I want to know these two loads and the distances that they're at. I'm going to assume this is the positive direction. I'm going to find that number. So I'm going to go a distance of 1 minus a third plus 0.1, and then just minus 0.5. So I went positive 1, I subtracted this. Subtracting a negative is adding, and then I subtracted a half. Cool. And again, just decimal answers for these. 1 minus a third plus 0.01. And I guess I'll spell it out. So 1 minus a third plus 0.01 minus 0.5. I'm going to store that as alpha A. So I got 0.176 repeat. Cool, let's switch it up. This is positive. I'm going to find this distance. So I'm going to use this method. So I'm going to go just knowing that this distance is the same there, this is the same there. And now I can even see, like, if I add this to this, this has a negative, this has a positive. So if I'm adding these go away. So hell yeah. So this, literally this distance is just 2/3 minus a half. Okay, sweet. And that's going to be 2/3 is 4/6 minus 3/6. That gives me a sixth. So that distance is a sixth, and I'm going to store that as B. So we're still kind of in that same. Well, let's see. So this, what did we do? We did A first. Hell yeah, that's the bigger number. So A was bigger, and so this distance is farther than, this is 1/6, and this is just a little bit bigger, so it's not going to tip over. If we have this book farther out away from this tipping point, this kind of axis, kind of the center of a teeter-totter, then it will tip over if that's farther this way. But in this case, I just don't have it drawn very well because I actually subtracted this. This load of this book should be farther that way. It is, and so that means we can move this whole system just a little bit that way. So let's see how far we can move it. So we're going to go alpha A plus alpha B, and this we need to divide by 2. Cool. So this is the distance that I can move it this way, and so that's well, no, that's the center. So I added these two up, divided by 2. That's where the equal distances should be. So we said that this one was a little bit, this was 1/6, but we can get it out to this value. I'm going to store it as alpha D. We can get it out to there, so we can move it just this amount. That's going to be alpha D minus a sixth. So this, and we can move it 0.005. Hell yeah. So I don't know, maybe we can optimize this. I can't imagine. So now we're going to figure out what this distance is, and knowing we can move it 0.005 just a little bit more. So let's do that. Yeah, so what is alpha D? Well, didn't we just say it's going to be this plus this? Isn't that 2/3? And then we can move it 2/3 plus 0.005. So can't we? Yeah, so 1/3 I don't think is the answer. I don't know, unless I made a mistake. But no, we can optimize this just a little bit more. So let's yeah, is that true? Let's go back over this. If this is the positive direction, I want to know this distance, and that's going to be 1 minus a third plus 0.1. Sorry, plus 0.01 plus, minus 0.5. Minus 0.5. So that's that distance. We stored that as alpha A. That's bigger than alpha B. This distance is really easy to see. It's just 2/3. Well, this was 2/3 minus 0.5, which is 1/6. And so, heck yeah. So we can move this whole system that way. And booyah. So now we have a problem that we can... this is interesting. So now I'm curious how much we can move it. And I feel like I'm doing something wrong at this point. But that's the whole deal, is just like, hey, just do something, change it a little bit. So now how would I change it without freaking out? I think that I don't know what I would do. Well, actually, right now, I feel confident that I could set up an equation, because the whole idea of doing this process is we've ran through these numbers so much. We've done the same exact things with the numbers. We tried to find a distance, and then we tried to find another distance. If they weren't the same, then we did something else. So now I think we can figure out, an optimization. So I'm going to say what D... Well... Oh, this is a bummer, because if I say what D is, well, this x term is going to cancel out. It's just going to be 1/3 plus 1/3. So then I need another term in here that adjusts. Let's go through this. This is fascinating even for me. So if I have this set up, and I know that if I input a little bit of x, I get a better output. And so I could just do it again, where I input, I could say x is 0.02 and see if I get the same output. Then I could do x is 0.05, then 0.1. And at some point I don't get a better output, and then I could go back the other direction. So that's what I kind of did to get to this point. But then I guess you get to a certain point, and even like right now, I guess I don't want to do that. I don't know why I don't. Yeah, I think we should do it at least one more time to get the hang of it. So we're going to say, hey, this is a pretty good way to go. And so I got a third minus an x. So I'm going to go 1/3 minus 0.02. And then here I'm going to go 1/3 plus 0.02. And I'm going to solve for the distances to those two loads. And so that should be pretty easy. Positive direction, it's going to be 1 minus 1/3 plus 0.01 minus 0.5. So, and we're going to call that A in the calculator. And then just kind of doing the same things is very useful. Alright, so 1 minus 1/3 plus 0.02, because we might have made a mistake too, so it's just always good to go over it again. So there's our A, and heck yeah, A is nice and big like we would expect. And again, B is going to be the same thing. It's just going to be this distance plus this distance, but these cancel, right? Because we would have 1/3 minus 0.02 plus 1/3 plus 0.02. So those cancel, and then subtract 1/2. So that gives us that 1/6 value. So B is 1/6. And then we did the A plus B divided by 2. This is the distance that that B could be. So B is at a 1/6 from the hinge. It could be a distance of this A plus B divided by 2. So once we know that this distance, see what I'm doing here, we've done the calculations so much, now I'm trying to make an equation. So once I do A plus B, the distance between the two books in this setup, and then I find the distance in the middle, that's just the distance from this point out to there. which is going to be bigger than a 6. So this is going to be bigger than a 6. So I'm going to take this, that, minus a 6th. And this is the distance that I can move this whole system that way. It's going to be the change in d, or just the plus d that I get. It's kind of that little extra. So sweet. So what's the equation here? What's the equation for plus d? That's going to be a plus b divided by 2 minus a 6th. Hell yeah. And then, how did I get a? Well, I took this, I got a from 1, negative 1, what did I do? Yeah, no, 1 minus this minus that. No, I'm sorry. I got to a plus 1 minus this minus a 0.5 gets me that distance. That was a. B was this plus this minus 0.5. Cool. All right, but we have a and b in our calculator, so we're going to go a plus b divided by 2 minus a 6. And hey, that gives us 0.01. So now whatever this distance was, d, I can improve it to 0.01. Okay, hell yeah. So let's do that. So this distance was going to be 2/3 plus 0.01. So now we're up to 0.656. And this is interesting. I swear, like from this morning, I thought the answer was 5/4. No. I thought the answer was 4/5. Is that right? 4/5? 4 divided by... No, I thought the answer... I don't even know what... Like, honestly, I don't even know what I thought the optimized answer was. But that doesn't matter, because the whole idea of this video is, like, if you can do one equation, if you can just throw in the numbers for one scenario, just do it on repeat just by changing something, and what falls out in the wash is the actual equations that you're building. I mean, if you're just constantly doing the same things with the numbers, that's an equation. You know what I mean? And then if you're taking that number and then doing a couple more things with it, well, that whole system is an equation. And then so you can take that equation, and so now what we can do is, like, well, we basically have this equation for plus d. And the way that we have it set up, if we're choosing 1/3 and then adding a number and subtracting a number. All right, hell yeah. And I thought I had the answer this morning, and I guess I just didn't. And this is so fascinating. But it is, we're doing from a numerical method exactly what I wanted to do. I just got to the point that, just adding 0.01 and then adding 0.02, well, hell yeah, we're getting a better answer. So let's keep adding, but let's not go to 0.03, 0.04. Let's really kick it up. And for this one, I mean, it's kind of cheating to do this, but just because there's a lot of problems where you're not able to use a example to represent, where I think what I'm showing here is using numbers to do the same thing that you would do here, just kind of experimenting with, hey, what's better? So that's why, and this is kind of the derivative process, but for the life of me, I struggle with seeing what equation I'm making, like this plus d equation, but I'm getting close. But even here, it's just like, well, why would these two things need to be the same? This 1/3 and 1/3, those don't need to be the same. Or they don't need to be, oh yeah, that's interesting. I guess this now is just becoming an arbitrary number, and if I subtract and add, then I can get any difference between these two. I think that's the case. Even though I'm starting at 1/3 of the distance, if I is that true? From a mathematical perspective, let's say I have 1/3 of the distance here and there. If I subtract a little bit here, but then add a distance there, can't I get any number for this as I could for this? Because I could just keep going, you know what I mean? And then I could get that ratio, keep going. I could get that ratio, keep going. And can't I get any ratio between... yeah, that's fascinating. I think, man, my hardcore math isn't very good. That's why I struggle with equations. That's why I use numerical methods like all the time. So that, enough said there, but check this out. So if we start from that 1/3, Like I thought this was a pretty good deal. But it just makes it tip over right there. And honestly, like I can get this one halfway if I wanted to. But so what we're doing is we're subtracting this distance and seeing if we can add more. And we can add just a little bit more. So let's subtract this. And then we can add, whoa, look at that. Visually, you can even see how much more you can add. That's crazy. So then I'm going to subtract a little bit more. And then I'm just going to, okay, so that seemed like the optimized position. Let's go back and see if I can, you know, so there you go. So let's actually get, you know, where I think this is right there. I think that's optimized. So now let's move it this way and see if I can get there. No, it's going to tip over way early. So now I'm going to try to optimize this way. I'm going to go this way, and I have to be like right there. I can keep going. See, now I can keep going this way until this thing falls off. Oh yeah, so this is interesting. I mean, basically what I have right here is this at the halfway point. And maybe I did not see that scenario. So this one is at the halfway point, and then this one is just right where it wants to tip over. So that's just right about there. Cool. And do I get? I think I actually get just a little bit more. It's really hard to see if I move this. Okay, so that could be optimized, and I think even from our equation, even though that we have this random 1/3, you know, because 1/3 is out here and we're subtracting to get to this, and then maybe we're adding to get to that. So I think we're gonna, I think we'd miss that. But let's see if we move this one this way. We have to move this one back. And so now we're balanced right there. And that's clearly less. So yeah, I was wondering if this problem had one point of optimization or a couple. But yeah, so that's optimized right there, where if I move this back, man, I can just really juice this out. So that's, well, it seems close. Yeah, it seems like it's hitting about the same point. So I'm going to go this way and then in. Okay, I think, well, that looked pretty, that looks better actually. Yeah, for whatever reason, that one looks sweet. Yeah, right there seemed amazing. Where if I go this direction and then back, okay, I lost it. Anyway, so what we're going to do is that same process by using our equation. This equation doesn't seem that legit, but let's try it out. All right, hell yeah. So same scenario. We're going to have 1/3 minus x, 1/3 plus x. We're going to have some distance, you know, to that load on that book, some distance to that load. Let's see if we can now just thoroughly do an equation. We know that this is also going to be 1/3 minus x, 1/3 plus x, and we know that we know that d in this scenario is actually going to be 2/3. So we know that's going to be d. But we know that this load is going to be farther that way, so we can move this load is typically always going to be bigger in this scenario. I mean, this distance to this load is going to be farther that way, so we can move the whole system. And so that's the equation that we did, and that amount that we can move the system we call just plus d. So now that we know the d optimized, let's just call it d op or d max maybe, is going to be this d 2/3 plus, You know what I mean? And I'm just going to call this the change in D. So plus D, kind of that thing, that juicy thing that we want, that's going to be just the change in D. Okay, and we had an equation for that, but let's do the whole motions. We're calling this A, and then this B. Once we get A and B, then we took A plus B divided by 2. And we knew that B was always 1/6 in this scenario. Cool. So, and I'm baffled and fascinated at the same time that I can keep moving forward, but that for the life of me, I do not know how to set up an equation. Like, I don't see it. Like, I don't see the optimized equation, what variables you put in. You know what I mean? I would imagine, do you have to call these two different variables, like x and y? Do you have to use, like, partial derivatives if that's the case? I just didn't know. So I just wanted to just try to go for this problem from a numerical perspective, so that's what we're doing. Okay, so hell yeah. Once we get that distance, we'll have A plus B, and that's the distance between these two loads. And then we want to know the halfway point. Cool, that's going to be this. This is kind of the halfway. We even call it M for the midpoint. Once we know that, we know that this M is going to be bigger. M is always bigger than this B, 1/6. So we can move B that way. You know what I mean? So we can actually move these two blocks just that way. Because we've already said that if we get these two top blocks where they're balanced, we can for surely move the whole system that way if we can, if this is the tipping point to get the axle, get these loads evenly on both sides. So the amount that we can move that's going to be that change in D. It's going to be this M minus, is that right? M minus 1/6. So there you go. So that change in D is going to be A plus B divided by 2 minus 1/6. Hell yeah. And then so our D max is going to be 2/3, because we already know that, plus this, A plus B divided by 2 minus 1/6. So we're going to have 2/3 minus 6. We kind of clean this up. This is going to be 4/6. So 4/6 minus 1/6, that's 3/6. So, oh, that's wild. So 2/3 minus a 6 is a half. That's hard for me to see. This is 4/6 minus 1/6. I got to do the oranges thing. 4 minus 1 is 3. So sweet, we got 3/6. We got a half. So we're going to have a half plus A plus B divided by 2. But now we for sure need to know what A is. And so from this person, and we might lose our X value. We probably do. That'd be a bummer. I don't think we do, though. Okay, same thing. We're going to start from here. I'm going to call this the positive direction. I want to know A. So A is going to be positive 1 minus a third minus X minus a half. So sweet. So that's going to be A. And what is that? That's going to be 6 minus 2, 6 minus 6 X, or just X, I guess, and then minus 3, 6. So I have 6 oranges, minus 2, minus 3. So 6 minus 5 is 1. So I got 1/6 minus X. That's what I have for A. Hell yeah. Now B, I just have 2/3, because I have, whoa. The distance here, we're going to call this the positive direction. I have this plus this, and that's what equals 2/3, because the x terms cancel. So I have 2/3 out to there minus, What am I trying to, to here. So 2/3 minus a half. There you go. So let's say that's 2/3. That's going to be 4/6 minus a half. That's 3/6. So 4, and hell yeah. So B is always the 6th. And hopefully we don't lose our X term. So I'm going to have A plus B. And because that's what I'm trying to do right here. That's going to be 1/6 minus X plus 1/6. Okay, hell yeah. We don't lose our X term. So we're going to have 2/6. I'm going to call that 1/3. No, I'm going to call it 2/6. So we have 2/6 minus X. That's what that is. And then we, no, I should call it 1/3. Yeah. So it's going to be 1/3 minus x, because now we needed to go a plus b divided by 2. What's that? That's going to be 1/3 times 2 minus 1/2 x. So I just took the 2's downstairs, and we get 1/6 minus 1/2 x. That's that term. Cool. So that'd be right here. So here we go. So d max is equal to 1/2 plus 1/6 minus 1/2 x. I deeply think I messed up. Alright, hell yeah. So I don't think I messed up, but I think, you know, we don't get something like an x squared where we actually have like a, oh, never mind. No. I don't know anything about differential equations. Holy hell. No, this is our, no, we're good to go. Because this is our equation for the d max. And what we want to do is find the change, the derivative, the change in d max when we change our x. Where we can't change our x any to get a better d max. And if this is d max, well, that's when x is 0. So, what? Huh. That's interesting. Yep. So I'm confused at this whole idea. Like, I think we did something. We might have done something fundamentally wrong. And the answer is just 1/3. But I don't think so. Let's go back to this. This is really fascinating. Let's go right up to here and then see kind of what answer we get. So this would be maybe where 1/3 and 1/3 and 1/3 is. So we're pretty close there. And it's really hard for me to see, but there's 1/3. I'm going to say 1/3. Now if I move this one this way, I swear like I could probably get more juice out of it. It seemed like I could get just a little bit farther. And so that one is way out there. And now I can get this one right there. So that is just visually farther. So that's wild. And does everything apply? Like if here is the pivot point, I have a load that's in the center right there. Hey, that's that distance away. And then I have a load that's in the center right there. Hey, that's that distance away. So sweet. So those distances are the same. And I guess what we're trying to maximize is this distance. Like the distance to this center. The farther it can be, the better. Yeah, that's kind of interesting. And is it set up where this is halfway? Like if this one's just right at that tipping point, I guess I just never did that scenario. Like I said, oh yeah, that's really fascinating to me. So that one is pretty much like kind of right at the halfway point. Yeah, it's definitely at the halfway point. And so what we're going to do is, it's really hard to keep it there. Okay, so now we're going to move this one, if we're able to. Yeah, so I can get this to the halfway. And that just right about there. So I'm going to get this halfway and then hold that. Oh, it's so ready to, wow, okay. I got it even farther. So, yeah, right there. This is the max. So we can definitely get it farther. And, yeah, that's just really interesting. Like, I'm bad at setting up, so yeah, this was dumb. You know what I mean? I guess going from 1/3 and then changing things, because we might not change things a consistent amount anyway. But if that's halfway, and this is kind of where it wants to tip, now the question is, well, let's try to move this one just a little bit this way. Now, does that mean that I can move this whole thing out farther? You know what I mean? Because that would be... And I don't think so. I think if I move it that way, I can't get to that point even. So that shows you that that is a true maximum. So I think there's only one location that actually has a maximum. I'm so glad I can play around with this problem because, yeah, I'm kind of bad at the equations, I think, just going for it. So, so see how if I move this one to the 50% right at tipping, then I can, I have to move this one back, but get this one right there ready to tip. And I can actually reach that point right there. But if I move this one in again and then move this one out, I can't reach that point. I think I'm still just shy. I would say that visually is about right there, where then if I move this one out and then that one back, hell yeah, I can for sure reach that point. Alright, pretty fascinating. So I think I'm going to go back to the drawing board and see if I can just come up with a differential equation. Alright, hell yeah. So I'm back and I calmed down because I got to a point where I was just saying wrong things down here. We came up with an equation for D max. And yeah, so we're just going to go over that one more time because this was working out. And it was just kind of fascinating. So, I mean, we got to a point where if these were even Steven, yeah, we could do a third and a third. But then we were saying, you know, the whole point of this is just like, hey, do one thing. And so so if we recap of what we did, we said that if we just pay attention to the top two books, we could go a half, and then they're supported. If we put the bottom two books together and put the top book up here, we can also go a half. So, but then the question was, well, if we move this one this way, well, can't we increase that? And that's probably... but I did not see that right away to be like, hey, if I get this one to its point, how far can I get this one? And that would have been the place to analyze first, to be like, okay, I could probably do an equation. Just keep this as a rigid system and then move it until, you know what I mean? Because this has a center of mass, so you can see where this mass is. It's not at half. It's, you know what I mean, it's at 3/4. So there you go. So I think I'm kind of just learning on the fly, but I would look at this top system as having a weight of 2p that's directed right at 3/4. So this point has to be directly over the pivot. So now I can, but I'm so glad I went through that whole process because that's what we're talking about. It's really difficult to just look at an equation and be like, oh, I know exactly what's going on. And then even just playing around with this, I knew I could get farther than a third, I just didn't know why. Or I could get farther than 2/3. So now I'm going to, you know, even going from here, this was a fine way to do it. You know, I got 0.33 repeat for both of these. But then the question is, especially when it comes to optimization, is to do that same strategy that we just did. Well, like, can I increase this one? You know, can I push this one that way? Sure, but I gotta move this one that way. Because we're saying if these are 1/3 and 1/3, hey, our balance points right here, these are even Steven. So if I do move this block that way, well, I gotta move this whole system in. But when I do that, it just happens. What happens is that this distance just remains 1/6, and this distance really increases. So yeah, I can't, like, even from this little diagram, I can't visualize that. But let's talk our way through it again. So with this setup, with changing x, like reducing this and then making that go out, and it gives you a little bit extra. And so the first thing that we solved for was this A, this distance right there. The second thing we solved for was B. So let's go back, and so A, I said A was going to be a positive 6/6 minus 2/6 minus minus a minus, so that's going to be plus x. And then we have minus a half, that's minus 3/6. So I have 6 minus 5. So that's going to be 1/6 plus x. So this b term, we said it's going to be this plus this. The x's cancel. It's going to be 2/3 minus a half. That's going to be 4/6. That's 2/3, right? And then minus a half, that's 3/6. So 4 minus 3 is 1/6. And b will always be 1/6. But, I don't really understand but I mean, we're going to get to an equation, and we're going to get to where we can find its maximum. Like some equations, like if your salary is y is equal to x, every day you get x dollars. Well, hell yeah, just keep working until you die, because every day you'll make more money. Like the maximum is the day that you die. You know what I mean? You won't be able to get that day's worth of money, so you'll get the day before's, and that's the money that you'll make. So there is no maximum point there, or their maximum point is the limit of how far you can take it. So even though our equation is just the fact that d max is 2/3 plus this 1/2 x, that's what we're getting to. Hey, just make x as big as possible. But then when we go back here, if this was a distance of 1/3, and then I'm going to increase a value of x, I can only increase up to 1/2 before this top one tips. And so that's kind of the foreshadow. All right, but let's go back to, we have this distance A, we have this distance B. And so now we're going to, so what we have, A plus B is the distance between these two loads. And so we want them to be centered. You know what I mean? We know one's 1/6 and the other one's bigger. And so we're going to add them up and then divide by 2. It's going to give the halfway point between them. That's where our tipping point wants to be. And so when we do that, when we go A plus B divided by 2, we're going to get a bigger number than 1/6. So keep that in mind. All right, so let's, so this was A, 4/6 plus x, 1/6 plus x. So let's do it. Let's do A plus B. And so, where do I do A plus B? I guess I do it right here. So that's going to be, did I even do it right? No, oh yeah, sorry. This is A and this is B. So 1/6 plus x is A. B is 1/6. We already came up with that. So if we add them together, we're going to get 2/6 plus x divided by 2. And then if we divide by 2, this 2 will cancel, and then we'll have a 1/2. So we'll have 1/6 plus 1/2 x. So hell yeah. So that's that term. Once we find that midpoint, which is going to be a bigger number than 1/6, we want to find the amount that we can move it that way. And so that's going to be, even visually it's hard for me to, but how do I have it written? Yeah, so this extra that we can move that is going to be A plus B, that bigger number, minus a 1/6. Yeah, the difference between those, because it can be at A plus B divided by 2. That's where this should be, but it's not. It's at 1/6, so we can increase that. So this minus that is the amount that we can increase, that plus D. So we're going to have that term, which is 1/6 plus 1/2 x. That's that. And then subtract 1/6. Cool. So now we just have 1/2 x. That is our plus D term. And so now we can go back to our equation. This D was 2/3, but we can't increase it. So it's going to be 2/3 plus that plus D term. And so that's what I have right here. D max is 2/3 plus 1/2 x. Well, hell yeah. Just like, just make x as big as possible. How big can x be? Well, that's why I have to analyze the top. X can go until 1/3 plus this extra value of x equals 1/2. Because if I'm already at 1/3, I can add up to 1/2. So 1/3 plus a number equals 1/2. Let's do that over here. That's going to be 1/3 is 2/6 plus a number is equal to 1/2. That's 3/6. So hell yeah, this is just getting this to the hell to the other side, and then we got 3 minus 2. So it's just going to be, that thing is going to be 1/6. So x is 1/6. That is as big as we can make x. And so in that scenario, we're going to have, oh cool, yeah. So in that scenario, we're going to have d max is 2/3 plus 1/2 times 1/6. This becomes 1/12. So we need to get this to be 12. We're going to multiply top and bottom by 4. That's going to be 8/12 plus 1/12. So 8/12 plus 1/12 is 9/12. Factor out of 3 is 3 times 3, 3 times 4. The 3's cancel, right? So this is 3/4. So d max is 3/4. That makes sense from our analysis. And let's go back and figure out what these distances were. So 1/3 plus x is going to be, what's our x term? Is 1/6. So we have 1/3 plus 1/6. That's going to be 2/6 plus 1/6. Whoa, okay, so that's just going to be 3/6, which is 1/2. So this term right there is 0.5, and we have a check on reality. Now how about this term? 1/3 minus x is going to be 1/3 minus a 6. That's going to be 2/6 minus a 6. Oh, whoa. Yeah, 2/6 minus a 6. Is that right? I feel like... Oh, yeah. So, yeah, perfect. So we still haven't solved the official problem. We're still back at... We kind of knew this was a little bit wonky. You know what I mean? But we can at least maximize one term, and that's what we've done. We've maximized that the top should be as far away as possible from this analysis. But the bottom, like this little term right here, though, is so we can analyze that as 2/6 minus a 6. That's still a 1/6. And we need to see if we can increase this. You know, if we increase this, does that help out? And that's the next thing we're going to actually check out. Because we had this 1/3 and we kept decreasing it. And then we moved our system. Yeah, and let's go back to this, because if this is at 1/2 and 1/2, well, hell yeah, this 0.75 can be right there, and then what would that mean? That would mean that this should be 1/4. So, all right. So how would we figure out how to optimize that? Because right now I have this scenario where I have, hey, this is 1/6. Don't know if it's maximized. This seems maximized. And this is still kind of like, this is like the worst way to do maximizations problems. But I'm just going through it because I'm learning a lot just by kind of repeating. This is going to be 1/2. You know, just doing the whole problem over and over again. So now I want to know what this A term and this B term is. I'm curious if those are even the same. They should be the same if it's optimized. If it's not optimized, hell yeah, let's just move it and see if it's optimized. That's the next thing we can do. So this A term, positive direction here, I'm going to say that 6/6 minus a 6 minus 1/2, that's 3/6. And so this A term, 6 minus 4 is 2/6. Sweet, or 1/3. Either way, and then the B term is going to be, well, B term is going to be this plus this. That's going to be 1/6 plus 3/6 minus... Alright, so that's going to be 1/6 plus 3/6 minus 1/2, that's minus 3/6. And of course we get 1/6. That was the whole point that wasn't like really optimized. So right now we have B is 1/6, A is 1/3. Oh yeah, I guess that's what we did. So part of this was like, hey, if... well, no, I don't know. I guess there was two things going on, and we were figuring out the second thing. But from this, we figured out what the optimal point was, because this equation, d max is 2/3 plus x. If this is what we have to work with, you know, if I have to start with a system that's 1/3 and 1/3, and all I can do is move this one that way and this one that way, equal amounts, well, Cool. I can move this one all the way to the halfway point, but then weirdly I'm just moving this one in the wrong direction. You know, that's all I did from this problem. That's why from here I can see from the mathematical perspective that I just figured, this just helped me figure out that this top one for sure has to be 50-50 split on both sides. And now I'm totally, well, I don't know if I'm, anyway, so, yep, so here's the difference between A and B. So we have A plus B is going to be this 2 6 plus 1 6. And we have a half. You know, I mean, we have 3 6. That's the gap here. We have 3 sixths. And halfway between that is going to be 1 point, you know, we should call this 6 twelfths. So halfway is going to be 3 twelfths. So half of A plus B is 3 twelfths. So this is what we can move this whole system that way. We can move it 3 twelfths. So we were saying that, so let's do that. So we were saying that D in this scenario was 1 6 plus 1 half. That's going to be 1 6 plus 3 6, which is 4 6. But we can actually move it 3 twelfths. So we're going to have 8 twelfths plus 3 twelfths, 8, 9, 10, 11. We're going to have 11 twelfths. So that's how far we can move. It still doesn't seem maximized. That's interesting to me. Yeah, if this is a half, the distance... Oh, this is tripping me out, because if this distance is a half, then A plus B has to be a half, right? Isn't that what I got? A plus B is a half. I think I messed something up here. Yeah, A plus B is a half, which is 3. Yeah, 3 6, which is 6 twelfths. Yeah, and this is a fourth. So I can move this whole thing 1/4. Is that what I have? So if this distance D right here, and in this setup is 1/6 plus a half, I can move it 1/4. I hope this is going to work. Holy Toledo. So we're going to have 2 twelfths plus 6 twelfths plus top and bottom by 3 twelfths. 6, 7, 8, 9, 10, 11. We have 11 twelfths. I don't understand. Oh, my bad. I totally forgot a step. You know what I mean? But that is where we're doing an equation just over and over again makes sense, because then you can catch your errors. So what we have here is this distance was always a 6 that wasn't very good, because this is a 6, that's a 6. You know what I mean? We can shift this whole thing that way. A is bigger than B, and yeah, A is bigger than B by quite a bit. You know, it's bigger than... So yeah, so and then the distance between A and B is going to be 2 6 plus 1 6. That's going to be 3 6. So, and that's going to be a distance of a half. And that's what we should expect, is if this is a half and this is a half, the distance between the centers is going to be a half. Cool. So, man, it's... What I would like to be able to do is just do it based on the pictures and equations. But I swear, I need something to look at sometimes. Because... okay, so yeah, that distance between A and B should be a half, but then half that distance is what this should be. So that should be a quarter. It's a sixth, so we can move this one this way, 1/4 minus a sixth. That's that plus D. That's the distance we can move that. So now we can say this is 3 twelfths minus 2 twelfths. And this is what we're going to move it. We can move it that way 1/12. So then when we go to analyze, we can say, hey, this is going to be, and hopefully, man, I even feel like I did that wrong. But yeah, distance between A and B is is a half, which is 6/12. And divided by 2, that's going to be 3/12. And how much we can move this is 2/12, so we can only move it 1/12. Okay, so D, what was D? D originally was going to be 1/6 plus a half, so we have 1/6 plus a half, but D max, what we can move it is plus a 12th. So now we should have the answer. We have 2/12 plus 6/12 plus 1/12. Oh, weird. Do we still get this answer? 6, 7, 8? No, now we get 9/12. Oh, no, duh. Yeah, we get 9/12. Yeah, I was getting 11/12 because I messed up, and I was just like, what's 11/12? But yeah, 9/12 is 3 times 3, 3 divided by 3 times 4. You know what I mean? 3's cancel. 9/12 is 3/4, and booyah, we have our answer. Man, that was brutal. But yeah, so D max can be 3/4. But at no point in this entire process have I looked in the back of the book to see what the answer was. You know what I mean? So that's where, I mean, the way I do things is absolutely brutal, and I swear sometimes I get dumber. But I get better at making mistakes, finding mistakes. I get better at fractions. Like, we worked on a lot of things today, so I definitely really appreciate that. Alright, hell yeah. But this one was a hard one to optimize, and I didn't see it right away, you know what I mean? So tonight I'm gonna work on this one just from a straight equation perspective to be like, hey, is there like one equation or 2 systems of equation that I can put together that I'm optimizing? How would I have figured that out? That we have a quarter of the distance there, half the distance here, and you know what I mean? And this reminds me of, like, it's bizarre, like, when you do things and then forget about them, because I swear now you can have as many books as you want, but I think the next book has to be a distance of a quarter, and that, like, we could probably do that here just from the perspective of now we know what the hell's going on, is that the next book would have to wherever the center of this mass is. So let's even do that, like, right now. It's kind of fascinating. And that's kind of how we'll close this out. It's a good thing to do, like, once you actually struggle through a problem, like, what did you learn? So we have a load at right there. I'm just going to call that right there. We have a load right there at 0.5. Hell yeah. And then the center of this one is just a quarter. So we got 0.25. So that's where our loads are. So if we actually had to find the center of this, you know what I mean? You would have to find the place where, if you balance this, if you put it right there, you would have like a moment. This thing would rotate that way. That's one way to look at it. So I'm just going to say, hey, there's a distance x here that can balance these loads. And we're going to have 3p here. And so what I do is I just sum the moments about any point I want. I could do right here. So we would have... Alright, hell yeah. And sometimes it's probably better just to do this in your calculator. It's less heady, you make less mistakes. So if I start here, this has a moment of 1 times a distance of 0.25. And let's not do it in our calculator. So we have a negative moment, 0.25. We have a negative moment that it's this distance. That's going to be 0.75 times this load. That's load of 1. And then we have a positive moment plus 3, a distance of x. So we have 3x. This is equal to 0. I could have just done, and then this is going to be negative 1. Negative 1 plus 3x is equal to 0. Get this to the other side, so we have x is 1/3. So heck yeah. So even just right there, well, what did we just find? We found that that these loads will act at a distance from where? From this point of 1/3. Does that even help us out? Yeah. Well, I mean, I guess from this point, it's saying that this whole system is just one or what are we saying? That almost doesn't seem right. Where did I start from? Did I start from over here? I went half. Well, no, I just put this one right at this point is like right there, and then I went over here and put the second CD, and then I went a quarter to put the first CD. And then, so from the center of this CD, or like tape deck, I have to go over 1/3, and that is where this whole business, like the center of this whole thing, rests. Because if I just had these two tapes, the center was right here. So from this deck, it was 3/4, 0.75, but from this deck, it's going to be, oh man, half, that's right here, and then a quarter. Yeah, so from the center of this bottom disc, I have to go a third. So that's going to be 3/6 plus 2/6. That's going to be 5/6. So, yeah, so all of, all right, hell yeah. So all of the weight happens at 5/6. So it's pretty much, if this is divvied up into 6, you know what I mean, which would be thirds, and then 6th. Yeah, all the load is right there. And so this would be the place where it would tip. So I can put all of this right at the end of the CD. So the end of the CD could be right there, because that's literally where all this load is driving through. And then so that means that this next one would be 1/6. I feel like that doesn't seem right. It seems like it should be, if this is a quarter, it should be like this, maybe like an 1/8. But, huh. All right, I'm going to walk through that analysis because I can see that I can get there. So these two cassettes, I have this one at the balance point, and that's pretty sweet. Okay, so the center of mass of both of these cassettes is at 3/4. It's going to be right there. What I can do is I can put that center right on this point, and that makes sense. If I put it to the right of that point, then it's going to tip. If I put it to the left, I guess it doesn't matter. I'm just not maximizing my situation. So that's where I can put it. Now if I have 3 discs, then I have to find the center of mass of these 3 discs, and I can put that on the edge of the CD. So then, so what I'll do is, I need some sort of reference point. So I guess I'm going to have this as my reference point. And the center of mass of this one is at 0.5. So I can just do this. So I can go, the center of this one is 0.5. The center, and we know that this is 0.25. The center of this one has to be 0.75 then. So that's what that means. And then the center of this one has to be 1.25. Because it's another 0.5. So 1.25. And I could have just started here. So to get to the center of this one, we got to go a quarter and then another quarter. So it's going to be 0.5. To get to the center of this one, I'm going to go, well, a quarter and then a half. That's going to be 0.75. To get to this one, I'm going to go a quarter, a half, and then a half. So that's going to be 1.25. So those are the numbers. Apologize. This one is a half. This one is 0.75, and this one is 1.5. So those are, from this point, those are the loads. And we have one at a half. We have one at 0.75, and we have one all the way out here. And so we need to figure out where we can balance these loads. We have more here, so maybe, well, if I balanced it right here, this one is farther away, it's going to cause this whole thing to tip, so I need to move at some point this direction. And so this is what I'm going to call X. Cool. Let's get this up here, and then start our equation. So this is going to be a negative moment, negative moment, negative moment. I know that I got to balance this in the y direction with 3p, and it has to be a positive moment. That positive moment has to equal the negative one. So we're going to say 3px has to equal these, which is 3/4. Damn it, I'm sorry. Which is 0.5p plus 1.25p. I missed that one. Plus 0.75p. Okay, so 1 1/4 plus 3/4 is 2. So I see 2.5. So we got 2.5p. The p's cancel, and I can say x is 2.5 divided by 3. That's going to be 5/6. So there you go. X is 5/6, and that's where the center of this thing would rest. That is where I can place the end of the cassette. So the cassette is going to be at 5/6 from this point. The cassette is 1 unit long. Yeah, the end of the cassette's right here. The cassette is 1 unit long, so this distance is 1/6. So I really don't know what the pattern is, but you could just continue this process, find a pattern, and then be like, no duh. But it's not a half, a quarter. It goes a half, a quarter, a sixth, and I'm pretty confident about that. All right, so yeah, this one was brutal, but I'm glad I at least did that last part and put another disc underneath it. So I think I'm going to be done. I'm going to go revisit this problem and see if I can get an equation that optimizes it without too much hassle. At the end of tonight, though, I'm totally going to go look up answers just to see how people do it the simple way. Because this one, for me, is just like, man, I can't see it. You know, it wasn't even a starred problem, but it's just like, it looks like the worst. So, anyway, so thanks for joining me on this one, and that's a video.